Welcome back. Today we're solving sum of total strength of wizards, a Leetcode HARD in C++ with the most optimized order n solution. Let's jump straight into the approach. Here's the task. For every contiguous subarray of the strength array, we compute its total strength, which is the minimum element in that subarray, multiplied by the sum of all its elements. We add that up over every possible subarray and return the answer modulo 10 to the 9 plus 7. With the array shown here, 5, 3, 1, 4, that's 10 subarrays, and the total comes out to 114. The obvious idea is to loop over every subarray, find its minimum and its sum directly, and add it in. That's order n squared subarrays, and with the constraints in this problem, that's simply too slow. So we're back to square one. We need a change in perspective. Instead of asking for the minimum of each subarray, let's flip the question around. Here's the key question. In how many subarrays is a particular element the minimum? Take element 1 sitting at index 2. It's the minimum in 6 subarrays. Now an element stays the minimum only until a smaller element appears when we extend in either direction. To the left of the 1, there are 2 elements and none is smaller. To the right, there is 1 element, then the array ends. So left count is 2, right count is 1. The number of subarrays where this element is the minimum is just left count plus 1 times right count plus 1, which gives 3 times 2 equals 6. So how do we find these boundaries fast? This is exactly the nearest smaller element problem, both the left and the right versions, and it's solved with a monotonic stack in order and total. Scanning with the stack, we find for every index I the nearest smaller element on its left at index x and on its right at index y. Those two indices mark the furthest our subarray can stretch, while the element at I is still the minimum, so our conceivable subarray looks like x dot 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 I dot 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 e. Now we need the sum of every subarray that includes index I and stays inside those bounds. Adding each one up directly would be slow again, so we bring in prefix sums. Let S of I be the running sum of the array up to index I, so S becomes 5, 8, 9, 13. Then any subarray sum is just a difference of 2 prefix sums. For example, the sum of 3, 1, 4 from index 1 to 3 is simply S of 3 minus S of 0, 13 minus 5, which is 8. Each subarray sum is now order 1. But there are still too many start and end markers to add up one by one. Yet when we write out the full sum over every valid start and end and then rearrange the terms, something beautiful happens. It collapses into left count plus 1 times the prefix sums from I to I minus right count plus 1 times the prefix sums from x to I minus 1. Now here's the second trick. What if we take prefix sums of the prefix sums? Define m of I as the sum of s of 0 through s of I, our double prefix sum array. Running the sums of 5, 8, 9, 13 gives m equals 5, 13, 22, 35. With the double prefix sum array ready, that whole thing collapses into one clean expression. The contribution of the element at index y is left count plus 1 times m of y minus m of I minus 1 minus right count plus 1 times m of I minus 1 minus m of x minus 1, all multiplied by the element's own value. That is order 1 per element. Remember to take the modulo along the way and add the mod back before taking it again so we never go negative. As a check, the 6 subarrays where 1 is the minimum contribute 1, 4, 9, 5, 8, and 13, which sum to exactly 40. Let's walk through the code section by section. First, we build the prefix sum array. Each entry is the running sum of the strengths up to that index, taken modulo 10 to the 9 plus 7. Then we prefix sum that array a second time in place. Now every entry holds the double prefix sum, the M array we derived. Next, a monotonic stack scanning from the right records the nearest smaller element on each element's right, the point where every subarray must stop on that side. A second stack scanning from the left does the same on the other side. Notice the comparison here is strictly less than, while the right side used less than or equal, So equal elements are counted exactly once and never double counted. Finally, we loop once over every element, read the left and right sums straight from the double prefix array, apply the formula, multiply by the element's strength, and accumulate, adding the mod back each time so the answer stays non-negative. And that's it. Prefix sums, a monotonic stack, and a double prefix sum, none of which ever exceed order n, so the whole solution runs in order n time and order n space, fully optimized. If this in-depth explanation helped, do drop an upvote and a like. Thanks for watching, and I'll see you in the next one.